Hi everyone, my name is Pablo Santiago Acevedo, and today I will talking about my source project. It was modeling fuel loss in nuclear thermal propulsion reactor fuel. First, to know a little about myself, I currently study in the University of Puerto Rico at Mayagüez. This upcoming semester, I will begin my 6th year of university. I am doing a major in mechanical engineering and two minors, one in aerospace engineering and another one in project management. My actual GPA is 3.51 and my estimated graduation date is May 2023. As my source mentors, Dr. Michael Tonks was my faculty mentor and Vishal K. Yadav was my PhD mentor. I work under the College of Engineering and the Material Science and Engineering Department. The objective of my research was to develop and run mesoscale models in UN nuclear thermal reactors and analyze the transport of free uranium throughout the fuel and metallic matrix. It will help NASA obtain guidance of how to design fuel to minimize fuel loss. To understand better this concept, a nuclear thermal reactor has a ceramic metal composite called cermet. Throughout the cermet, the fuel is flowing, which in this case is nitrate uranium or UN. Here you have the explanation of fuel loss. It is a microstructure change that occurs when the fuel particles are exposed to high temperatures by flowing hydrogen. In this case, the fuel particles are made of uranium. Once exposed, the free uranium particles transport through cracks and boundaries until it reaches a free surface area. Due to this, the uranium particles get vaporized, escaping with the propellant. It affects the efficiency of nuclear thermal reactor. These are the chemical reactions that occur when the UN is exposed to high temperatures and flowing hydrogen, resulting in the separation of uranium from the fuel. The right figure shows the behavior of free uranium. The free uranium is located first within the fuel particle and then it passes through the matrix. Since the left, right, and bottom corners have closed boundaries of zero flux, the free uranium reaches the top as it is considered as a free surface, allowing the free uranium to get exposed by the atmosphere and get vaporized. This is the diffusion equation, which was applied in the simulations. And the parameters used in the diffusion equation are the XU, which is the molar fraction or the concentration of free uranium in the material, T, that is the time, Du, that is the diffusion coefficient, Ru, that is the rate of free uranium generated by thermal dissociation in the UN fuel particles. Then we have the du equation, which is composed by the suction functions represented as h and the diffusion coefficients for each region in discernment. The regions are the fuel particle, matrix, boundaries, and cracks. For calculating the diffusion coefficient along fuel and matrix boundaries, the Arrhenius expression was used, and in the Arrhenius expression, the parameters used was d sub 0 and q, which are constant values, r, which is the ideal gas constant, and t, which is the temperature. Through some assumptions and modifications, the du equation becomes du equal to hf multiplied by dfg plus hm multiplied by dmg. It was since this because we didn't consider crack and boundaries in the simulations. So in other words, the value for the suction function for cracks and boundaries were 0 and were cancelled in the equation. In case of Ru, This was the equation used, in which A and B are constant values, hf is the suction function for the fuel particle, eta f is the value for the fuel particle region, R is the ideal gas constant, and T is the temperature. To perform the simulations, the most finite element framework was used. That is a combination of the software of Peacock and Atom, and also to obtain the models, the software of Paraview was used. After modifying the DU equation, coding was added to the fuel particle to analyze its impact in the simulations. The right image is a DU model obtained from one of the simulations. The extraction functions were added to the presentation to identify each region. In this case, Hm represents the matrix and 1 minus Hm represents the fuel particle and coding regions combined, but separately, Hf corresponds to the fuel region and Hct to the coding region. The simulations were realized by changing the value of the content of the coding thickness. As you can see, from 2 micrometers to 4 micrometers, the concentration of Xu outside the fuel particle and coating reduced to 0, but within the fuel particle it increased, meaning that a higher thickness will keep more concentration of free uranium within the fuel. In this graph, you can see that as the coating thickness increases, the fuel loss takes more time to reach steady state. Another analysis performed was keep the thickness constant as 4 micrometers and change the value of the diffusion coefficient for coating at each simulation. The new graph obtained showed that the increment in the diffusion coefficient for diffusion coefficient for coating will make the fuel loss to take less time to reach steady state. On these images, it can be seen that the increment in dCt, which is the diffusion coefficient for coating, decreased the concentration of free uranium within the fuel particle. As a summary, coating material was added in the simulation. Increasing the coating thickness decreased the fuel loss. Increasing the diffusion coefficient of coating makes the fuel loss to take less time to reach the steady state. In conclusion, the best solution to reduce fuel loss is increase the coating thickness because it will help keep a higher concentration of free uranium within the fuel. As future goals, I plan to apply for a PhD program at UF in the College of Engineering and the Department of Mechanical and Aerospace Engineering. If I got accepted, I hope to put in practice what I learned from the SURF program for the PhD research. In the section of acknowledgements, I want to acknowledge Dr. Tons for accepting me in his project and his feedback on my work. I want to acknowledge Vishal K. Yadav for guiding me as a mentor on all the skills and knowledge he taught me. I am thankful with the University of Florida for granting me this research experience. And finally, but not less important, I want to acknowledge Mike Nazareth for doing an excellent job as the coordinator of the SURF program. And also, I want to acknowledge NASA for funding the project of Dr. Tons. That's all. Thank you for your attention and have a good day.